Hello, and welcome again to Math Counting. Before you continue watching this video, make sure you have watched the previous videos on limit of functions. Right. So we said in the previous video that if we have a rational function, the limit of a rational function like this, so x squared minus x all over x squared minus 1. If we insert the limit point, which is 1, into the function, we are going to have 1 squared minus 1, 1 squared minus 1, and this is 0 over 0, which is an indeterminate form. Okay? Now, we can test what happens when x approaches 1 by simplifying the function. So if we factorize the numerator by saying limit as x approaches 1, x minus 1 all over x minus 1, x plus 1, then this cancels out, and then we have x over x plus 1. So now if we take limit of this function, we have 1 over 1 plus 1, which is 1 over 2. Great. So now, what if we have a function like this? We have a function like limit as x approaches 1 of ln x all over x minus 1. Or 2, we have a function like limit as x approaches infinity e raised to the power x over x squared. So realize that we cannot just factorize these two functions as we did for this function here, right? So now let's test these two functions with their limit points. So if we insert 1 here, solution for 1, if we insert 1, we have ln of 1 over 1 minus 1, and this gives me 0 over 0, which is also an indeterminate point. Yet I can't factorize it. So now, what if I have this? If I insert infinity here into this function, I have e raised to the power infinity over infinity squared. So for this function, we will see that the numerator will approach infinity faster than the denominator, or there is going to be a point where maybe we have a compromise where we can have an exact value, right? But what we can do here is we realize that the numerator is approaching infinity and the denominator is also approaching infinity. So we have infinity over infinity, right? Now, since we cannot apply the normal rules of limits onto these type of functions, according to L'Hopital, okay, so we are going to apply L'Hopital's rule. So according to L'Hopital, we can differentiate the numerator and then the denominator. So according to L'Hopital, suppose we have two functions, f and g, such that limit as x approaches a of f is equal to 0, the same thing for g of x equal to 0, then what we should do is to find the derivative of the numerator and then the denominator, right? So you can take your time and read through the theorem very well. So I'm going to rewrite the questions here and then we'll solve them one after the other. So for the first one, we have limit as x approaches 1 of ln x over x minus 1. So how are we going to do this? So we are going to say that let f of x be equal to ln x, and then I'm going to say let g of x be equal to x minus 1. Now f prime of x is equal to what? 1 over x, and then g prime of x is equal to 1, right? Great. So we are just going to insert them back And then we are going to say limit as x approaches 1 of 1 over x over 1, which is the same as saying 1 over x. So we are now going to insert our limit point, and then we have 1 over 1, and our limit point is 1. Our limit is 1, right? So it's quite simple actually. All we need to do is to differentiate the numerator and then differentiate the denominator, and then we take the limit as x approaches the limit. All right, so now let's look at the second one. The second one says limit as x approaches infinity of e raised to the power x over x squared. All right, we have already tested the limit point. So according to L'Hopital, we should let f of x be equal to e raised to the power x, and then let g of x be equal to x squared. Okay, so now we need to find f prime of x. F prime of x is still e raised to the power x. If you can't differentiate, please go and watch my videos on differentiation. So we have g prime of x, which is equal to x. Now, if we insert this into the function, we are going to have limit as x approaches infinity of e raised to the power x all over 2x. Notice that we still have x in both the numerator and the denominator. For that matter, if we insert the limit point, which is infinity, we are going to have e raised to the power infinity over 2 times infinity, which still gives us infinity over infinity, which is also what? An indeterminate form. Notice that we keep getting the indeterminate forms 0 over 0. We keep getting the indeterminate forms 0 over 0 and then infinity over infinity. So basically, once we have these indeterminate forms, we apply L'Hopital's rules. All right, so let's continue with this question. So now that we have infinity over infinity again, we have to repeat L'Hopital's rule on this question. Okay, so we let f of x. So, I think we need to find f double prime of x, which is the second derivative of f, which is now equal to e raised to the power x. And then the second derivative of g is equal to 2. So we insert it back into the function, and then we have limit as x approaches infinity of e raised to the power x over 2. So if we insert infinity now, we are going to have infinity over 2, which is infinity. Notice that this is not an indeterminate form, so we can actually end here, and our limit is at infinity. All right, let's look at one more. So we have limit as x approaches infinity of, this is infinity, of ln x all over square root of x. Obviously, if we insert the limit point, we have ln of infinity all over what? Square root of infinity, right? And what does this give us? To realize that we have the indeterminate form infinity over infinity. Therefore, we are allowed to apply L'Hopital's rule. So if we find f prime of x, which is the numerator, what do we get? So the derivative of ln x is what? 1 over x. And then if you differentiate the denominator, we have g prime. So g of x is equal, let's break it down a bit. It's equal to x raised to the power half. So g prime of x is going to give us 1 over 2 x raised to the power minus 1 over 2, which is the same as saying 1 over 2 x raised to the power 1 over 2. right? So we insert these two into the function, and then we have limit as x approaches infinity. Sorry, let me just move to all right. So then we have limit as x approaches infinity of 1 over x over 2 over 1 over 2x raised to the power 1 over 2, right? And this is the same as saying, we have 1 over x times 2x raised to the power 1 over 2, and then we have 2x raised to the power minus 1 over 2, and this gives us 2 over square root of x, right? So now if we insert our limit as x approaches infinity, clearly we are going to have 2 over square root of infinity, which is 0. So our limit is at 0, right? All right, let's look at another one, which is a bit different. So we have 3, which is, or 4. We should find the tan x minus x all over x cubed as x approaches 0. So if we insert 0 now, we are going to have 0 minus 0 all over 0 cubed. And we have the indeterminate form 0 over 0. Therefore, we can apply L'Hopital's rule, right? Great. So we can apply L'Hopital's rule. So we let f of x be equal to tan x minus x, and then g of x be equal to x cubed. Hence, f prime of x is equal to sec squared x minus 1, sec squared x minus 1, all over 3x squared, right? So now, if we take limits of this, so if we take limit as x approaches 0 of sec squared x minus 1 all over 3x squared, so we are going to get again we are going to get again 1 minus 1 all over what? 3, which is 0 over 0. Because sec squared x, sec squared 0 is 1. So we have again the indeterminate form 0 over 0, which means that we have to apply L'Hopital's rule again. So if we find a second derivative, which is f double prime of x, right? We are going to have 2 sec squared x tan x, and then g double prime of x is going to give us 6x. So if we put this in the limit form, we have limit as x approaches 0 of 2 sec squared x tan x over what? Over 6x. Good. So now that we have this, we know that the limit as x approaches 0 of sec squared x is equal to 1. For that matter, if we cancel this out, we are going to have limit as x approaches 0 of 1 over 3, right, times 1 times tan x over x, right? So if we continue, we can come down here and say that we bring the constant terms out. 1 over 3 limit as x approaches 0 of tan x over x. Great. So clearly, we need to apply Hopital's rule on this part of the function, right? So if we take this part of the function, we can say that limit as x approaches 0 of tan x over x. If we differentiate the numerator, we get sec squared x. So this is equal to f prime of x over g prime of x, limit as x approaches 0. And then we have equal to sec squared x over 1. Right? So if we bring this back into the function, we know that limit as x approaches 0 of sec squared x over 1 is equal to 1. So this gives us 1 over 3 times 1, which is equal to 1 over 3 from here, right? Good. All right. So now, considering these two types of indeterminate forms, another type of indeterminate form sprouts out of these two. Now, if we have two functions, if we have limit of two functions, like say limit as x approaches a of f of x is equal to 0, and limit as x approaches a of g of x is equal to infinity, then limit as x approaches a of f of x times g of x is not clear. Okay, the limit as f of x times g of x is not clear because it is going to give us this type, a limit of this form, 0 times infinity. So we have the indeterminate form 0 times infinity, right? When this happens, we will have to rewrite our limit functions so that it will resemble the indeterminate form 0 over 0 and infinity over infinity. Let's look at one example and you will understand clearly. So if we have a function like, say, you have to evaluate the limit as x approaches 0 of x ln x, right? So if we insert the limit point, we are going to have 0 times ln 0, right? And ln 0 is equal to negative infinity. So this is, because this is how the curve for the ln function looks like. Okay, so you realize that as the value x approaches 0, it approaches infinity. Negative infinity rather, right? So we are going to have the limit point of the form 0 times negative infinity. Okay, so how do we deal with such a problem, right? We can rewrite our function by saying that so we have limit as x approaches 0 from the right, x ln x can be rewritten as 1 over 1 over x times ln x. So that's lim as x approaches infinity from the right, ln x over 1 over x, right? So from here, we realize that if we insert 0 into the function, we are going to have ln 0 over 1 over 0. And this gives us infinity over infinity. 1 over 0 is infinity, right? So this is now in a known determinate form. And you guessed right, we can use L'Hopital's rule, right? Okay, so we now have this function. If we differentiate this function, where f of x is equal to ln x, and then g of x is equal to 1 over x, then f prime of x is equal to 1 over x, and then g prime of x is equal to negative 1 over x squared. So we insert it into the function, the limit function, and then we have limit as x approaches 0 from the right of 1 over x all over minus 1 over x squared, right? And if we simplify this, we end up having negative x, right? So if we take limit as x approaches 0 from the right of negative x, our answer is 0. Okay, so we will end today's video here on solutions of the indeterminate forms and L'Hopital's rule. Okay, and then I'll see you in the second part of this video.